Hello and welcome once again. We continue a series of lectures on discrete time signal processing. Last lecture we completed and we saw that the discrete time signal is extracted or rather sampled from a continuous time signal, and this has to be done in such a way that aliasing is prevented. And for that we saw that the discrete time frequency omega has to be between minus pi to pi, and depending on that we also have to think about certain frequencies called as the folding and the Nyquist frequencies, which will help us analyze signals in systems further. So now the maximum frequency that can be uniquely represented by a sample signal is called as the folding frequency. Now why did we come to the folding frequency, and why is it that it's essentially required for the sampling? Now this Fmax by definition is Fs by 2. Now this comes out because we saw that in order to prevent aliasing, capital F should be between minus Fs by 2 and plus Fs by 2. Also we saw that omega, that is the digital discrete signal frequency, has to be between minus pi and pi, also getting a restriction on Omax, which has to be between minus pi by t to plus pi by t, and hence the relation of pi fs. The Nyquist frequency is the frequency at which the signal samples. So obviously Fmax is Fs by 2, so therefore the Nyquist frequency is twice the maximum frequency of the signal. Now, having this knowledge of sampling and realizing the importance of the Nyquist and the folding frequencies, let's go to standard discrete time signals. The first one is the unit step signal. U of n equals to 1 for n equals to 0 and greater, and it's equal to 0 elsewhere. So mathematically you write it as U of n equal to 1 for n greater than or equal to 0. Now let's see a small variation in the unit step signal. So suppose you have u of minus n minus 1. Now here we make a certain set of tables. So let's say n is greater than 0 or equals to 0. So here you have u of 0 minus 1, which is u of minus 1, and we've seen from the previous slide u of minus 1 equals 0. Same thing applies for n equals to 1 and n equals to 2. However, if you take n less than 0, here you get u of 1 minus 1, which is u of 0, which is 1, and so on for all the negative values. So in general, if you see from these tables, u of minus n minus 1 will exist for n less, this should be less than 0 and 0 elsewhere. So u of minus n minus 1 equals to, yeah, you've got this correct here, n less than 0 equals to 0 else. Okay. Now, the second function is the impulse function. Now, what's an impulse function? It's a function which is the response of the system to an infinitely small change in the environment which it exists. So basically the infinitely small change is given by the impulse function. Now I would compare this impulse function to an identity identity number in mathematics. Say 7 into 1 will give me 7. So it's like an identity element. Or for that matter, in matrices, if you take I as the identity element, so any matrix multiplied by I will give you the same matrix. Okay, so it's like a unity element. Now, in discrete time system, this unity element is given in terms of the Kronecker delta function. The Kronecker delta function is treated also called as the unit impulse, given by delta, so delta n equal to 1 for n equals to 0. That means you are getting a small disturbance, infinitely small disturbance for you're giving a disturbance for infinitely small interval of time about n equals to 0. And that is how graphically it is represented like this, existing only at n equals to 0. Now, how do you manipulate these discrete time signals? So first one is a shift in time. So xn may be shifted in time and by replacing the independent variable n by n minus k. What happens if n is replaced by n minus k? Then k is positive, xn is shifted to the right by k samples. You get x of n minus k. Then this time shift is called as a delay of the signal. A delay is shifted to the right in time by mod k units, and the graph moves towards the positive side. Similarly, something called as an advance of signal. So when k is negative, xn is shifted by minus k to the left hand side, and you get x of n minus k, of that is x of n plus k. So x of n plus k is nothing but the advance of a signal, and time shift results in an advance of a signal. And shift to the left by mod k units, and the graph similarly moves towards the next negative side, that's the left side of the graph. Now, let's do this advance and delay in terms of the impulse function as an example. So delta n minus k is equal to 1 for n equals to k. So you see the impulse function at n equal to 0 is now shifted to n equals to k, and 0 elsewhere. Graphically, see, shift to the right. Advance of the impulse signal, so you get delta n plus k equal to 1 for n equals to minus k, shift to the left. So you have n equals to minus k. So you can shift all the signals, either delay them in time or advance them in time. The next is folding of a discrete time signal. How do you fold it? The operation is done by replacing the independent variable n by minus n. So basically it's a mirror image. So folding of a signal is done about the origin. So the mirror is at n equals to 0, and the reflection of the signal is about the time. Oh, yes, about the origin, n equals to the same thing here. And let's take an example. So x of n versus n equals 0. You've got only a signal which is to the right. Now you take this as the mirror and you reflect them and get it back to the other side. So here you get x of, and denoted by x of minus n. So you have at n equal to 0, the signal remaining same. X of minus 1 will now be the value of x of 1. X of minus 2 will be same as x of 2, x of minus 3, and so on. So you get x of minus n. Now, let's talk about a shift and a fold together. So a shift of xn, say to the right, is x of n minus k. A fold of a shift would be fold of x of n minus k. So whatever is here will be changed by a negative sign. So you get x of minus n plus k. So now let's see if we invert the two operations. So a fold of x of n is x of minus f. The shift of a fold would be shift of x of minus n would be x of minus n minus k. Now we observe that x of minus n plus k and x of minus n minus k are two different things. So therefore a shift and a fold, or a fold and a shift, are not two commutative operations. So if you have to do x of minus n plus k, remember that first the fold and then the shift, not the shift first. Otherwise, you would get a wrong answer because the sign of k is different. A fold and a shift are not commutative operations. Now, having understood these discrete time signals, we would therefore go to the characteristics of discrete time systems, which we would do in our next lecture. Thank you.